Introduction to Defense in Depth. Welcome to our comprehensive guide on GCP network security and data exfiltration prevention. Today we are going to explore the critical concept of defense in depth, a security strategy that is absolutely essential for the GCP network specialty exam. Think of defense in depth like protecting a medieval castle. You do not rely on just one wall. You have multiple layers: the moat, the outer wall, the inner wall, the keep, and guards at each level. Similarly, in GCP, we build multiple overlapping security layers. This is not just about one firewall or one product. It is about creating a comprehensive security architecture where if one layer fails, others are ready to protect your infrastructure. The 5 layers of GCP security. Let me walk you through our 5-layer security model. Each layer addresses different types of threats and attack vectors. Layer 1 is network segmentation using VPC firewall rules. This is your internal traffic control. Layer 2 is perimeter hardening with CloudNAT and CloudArmor, protecting your network edges. Layer 3 is the game changer. VPC service controls for data exfiltration prevention. Layer 4 covers secure API access through private Google Access and Private Service Connect. Finally, Layer 5 is IAM, controlling the human element because, ultimately, people configure all these security controls. Notice how each layer protects against different threat vectors: external attacks, lateral movement, data theft, API abuse, and insider threats. VPC Firewall Rules Fundamentals. Now let's dive deep into Layer 1, VPC Firewall Rules. These are your first and most fundamental layer of network control. Here's what makes them special. They are stateful, which means if you allow outgoing traffic, the return traffic is automatically allowed. Every VPC has 2 invisible rules with the lowest priority of 65,535. An implied deny all for ingress, and an implied allow all for egress. This is crucial for the exam, so understand these implicit rules. The key insight is targeting. You can use network tags or service accounts. Service accounts are more secure because changing a virtual machine's service account requires more permissions than changing its tags. 3-tier architecture example. Let me show you a practical example that is common in both real-world scenarios and exam questions. The 3-tier web application. This diagram shows how we implement the principle of least privilege. The web tier accepts traffic from the internet, but the app tier only accepts traffic from web servers, and the database tier only accepts traffic from app servers. Notice the firewall rules. Rule 1 allows HTTP/HTTPS from anywhere to web servers. Rule 2 allows port 8080 from web server tags to app server tags. Rule 3 allows port 3306 from app server tags to DB server tags. This prevents lateral movement. For example, if a web server is compromised, the attacker cannot directly access the database. They would have to compromise each tier sequentially. Implementing firewall rules with G-Cloud. Here are the exact G-Cloud commands you'll need for implementing our 3-tier architecture. I always start by creating the VPC in custom mode. This gives us full control over subnet CIDR ranges. Notice how I'm creating separate subnets for each tier with non-overlapping CIDR blocks. The firewall rules follow the principle of least privilege. Each rule is as specific as possible. Pay special attention to the service account alternative at the bottom. This is more secure than using tags, and the exam often tests your knowledge of this preference. The key exam tip. When targeting firewall rules, service accounts are always preferred over tags for security reasons. CloudNAT for secure egress. Moving to Layer 2, hardening the network perimeter. The first component is CloudNAT, which solves a critical security problem. How can private instances access the internet without being accessible from the internet? CloudNAT is a managed service. You don't provision any virtual machines for it. You enable it on a cloud router, and it provides outbound internet access while blocking unsolicited inbound connections. This is essential for security because it minimizes your attack surface. Your private instances can download updates and access external APIs, but attackers can't directly reach them from the internet. Cloud NAT architecture. This diagram shows exactly how Cloud NAT works. Your virtual machines in the private subnet have no external IPs, but they can make outbound requests through the cloud router and NAT gateway. The magic happens with stateful connection tracking. When virtual machine 1 makes an outbound request, the NAT gateway translates the source IP and tracks the connection. Return traffic is allowed back to the original virtual machine, but new inbound connections are blocked. Notice the red X showing blocked unsolicited inbound traffic. This is what makes Cloud NAT so powerful for security. It's a one-way door. Your virtual machines can reach out, but the internet can't reach in. Setting up Cloud NAT. Here's how to implement Cloud NAT step by step. First, you need a cloud router. This is required for Cloud NAT to function. The router handles the routing decisions, and the NAT gateway handles the address translation. I'm showing you two approaches: auto-allocated NAT IPs for simplicity, and reserved static IPs for when you need predictable external addresses. The static IP approach is useful when external services need to whitelist your NAT IPs. The key command parameters are NAT all subnet IP ranges, which means all private subnets in the region will use this NAT gateway. You can also be more specific with NAT custom subnet IP ranges, if needed. Cloud Armor. WAF and DDoS protection. The second component of perimeter hardening is Cloud Armor, Google's web application firewall and DDoS mitigation service. This protects against application layer attacks that firewalls can't catch. Cloud Armor integrates with the global external HTTPS load balancer, filtering traffic before it reaches your backend services. It includes pre-configured rules for OWASP top 10 attacks, custom rule language for complex filtering, and always-on DDoS protection. What makes Cloud Armor special is that it operates at Google's edge locations worldwide, so attacks are blocked close to their source, not at your backend infrastructure. Cloud Armor integration. This diagram shows Cloud Armor's position in your architecture. All traffic, both malicious and legitimate, first hits Cloud Armor at Google's edge locations. Cloud Armor analyzes the traffic for malicious patterns, applies rate limiting, checks geo-blocking rules, and filters out attacks before they reach your load balancer. Only clean, legitimate traffic continues to your backend virtual machines. Notice how attacks are blocked at the edge, while legitimate traffic flows through to your global load balancer and then to your web servers across multiple regions. This distribution ensures both security and performance. Configuring Cloud Armor. Here's how to configure Cloud Armor with comprehensive security rules. I start by creating a security policy, then add rules with different priorities where lower numbers have higher priority. Notice the rule priorities. 900 for allow rules, 1000 to 2000 for deny rules, 3000 for rate limiting. The rule expressions use Google's advanced rule language. Evaluate preconfigured EXPR for OWASP rules, and custom expressions for rate limiting. The rate limiting rule is particularly powerful. It bans IPs that exceed 100 requests per minute for 10 minutes. This protects against both DDoS and application layer attacks. Finally, you attach the security policy to your backend service. This is crucial. Cloud Armor policies must be attached to backend services, not directly to load balancers. VPC service controls. The game changer. Now we reach layer 3. Arguably the most important and powerful security control in GCP. VPC service controls creates a service perimeter around your projects and services, preventing data exfiltration. This addresses a critical threat that traditional firewalls can't handle: a compromised virtual machine or malicious insider trying to copy data from your private cloud storage bucket to an attacker-controlled bucket. Since this traffic never leaves Google's network, Firewall rules can't stop it. VPC service controls creates a virtual, policy-enforced fence around your sensitive resources. Think of it as a force field that data cannot cross without authorization. Service perimeter protection. This diagram illustrates the power of VPC service controls. Inside the service perimeter, we have trusted projects and protected Google services like cloud storage and BigQuery. A compromised virtual machine can still access internal resources. That's normal and necessary for applications to function. But when it tries to exfiltrate data to external resources like an attacker's bucket, VPC service controls blocks the request. The key insight is that this protection works regardless of network connectivity. Even if the attacker has compromised your virtual machine and has valid credentials, they cannot move data outside the perimeter. Notice how legitimate internal access continues to work while cross-perimeter data exfiltration is blocked. This is the beauty of VPC service controls. It stops data theft without breaking legitimate workflows. Implementing VPC service controls. Here's how to implement VPC service controls step by step. First, enable the Access Context Manager API. This is the service that manages service perimeters. Create an organization-wide access policy, then create perimeters within that policy. Notice how you specify both the projects to protect and the services to restrict. The restricted services list determines which Google APIs are protected by the perimeter. Access levels are optional but powerful. They create gates in your perimeter fence. For example, you might allow cross-perimeter access only from corporate IP addresses or managed devices. The monitoring commands at the bottom are crucial for operations. They help you identify when VPC service controls blocks legitimate traffic that you need to allow. Perimeter bridges. For complex organizations with multiple environments, you might need perimeter bridges. A bridge creates a trusted, bidirectional connection between two specific service perimeters. In this diagram, production and development perimeters can communicate through the bridge, but both remain protected from external resources. This allows you to maintain separation between environments while enabling necessary data flows. The key point is that bridges don't weaken security. They only enable communication between explicitly trusted perimeters. External attackers still cannot access resources in either perimeter. Private Google Access versus Private Service Connect. Layer 4 focuses on securing access to Google APIs. You have two main options for keeping API traffic on Google's private network rather than the public internet. Private Google Access is the simpler option. Enable it on a subnet, and virtual machines route API traffic through special IP ranges. But it's all or nothing. Once enabled, virtual machines can reach any Google API. Private Service Connect is more granular and secure. You create specific endpoints for individual services, and these endpoints have private IPs in your VPC. This means you can apply firewall rules to control which virtual machines can access which APIs. For security-sensitive environments, Private Service Connect is the preferred approach because of its granular control capabilities. API Access Architecture Comparison. This diagram clearly shows the difference between the two approaches. With Private Google Access, the virtual machine sends all API traffic to the generic private.googleapis.com endpoint, and you cannot control this traffic with firewall rules. With Private Service Connect, you create specific endpoints for each service you want to access. These endpoints have private IPs in your VPC, so you can write firewall rules to allow app servers to access storage but deny web servers access to BigQuery. The granular control of PSC makes it the modern, preferred approach for enterprises that need strict control over API access patterns. Configuring private access. Here are the commands for both approaches. Private Google Access is simple. You just enable it on the subnet and create virtual machines without external IPs. They will automatically use the private Google endpoints. Private Service Connect requires more setup but provides much more control. You create forwarding rules that represent specific Google services. You can assign specific IP addresses or let Google assign them automatically. The firewall rules shown here demonstrate PSC's power. You can allow app servers to access storage while explicitly denying web servers access to BigQuery. This level of control is impossible with private Google access. IAM. The human layer. Layer 5 addresses the human element, controlling who can configure all these security controls. Even the best technical controls are useless if the wrong people can modify them. The key networking IAM roles follow the principle of least privilege. Network admin has broad powers and should be granted sparingly. Security admin can manage firewalls and security policies but not network infrastructure. Network user can create virtual machines but cannot modify the network itself. This separation of duties is crucial for security. A developer might need network user rights to deploy applications, but they shouldn't be able to modify firewall rules or create new subnets. IAM roles architecture. This diagram shows how different IAM roles map to different responsibilities and resources. The organization admin has broad control but should be limited to a very small number of people. At the project level, you separate concerns. Network administrators manage infrastructure, security administrators manage protection policies, network users create applications, and DNS administrators manage name resolution. Notice how the network user role can create virtual machines that attach to subnets but cannot modify the network itself. This separation is critical for maintaining security while enabling developer productivity. IAM configuration examples. Here are practical examples of IAM configuration for network security. Notice how I'm granting roles to specific users and service accounts based on their job functions. The custom role example shows how you can create more granular permissions when the built-in roles are too broad. This automation service account can view networks and manage firewall rules but nothing else. The shared VPCs examples at the bottom are particularly important for the exam. In shared VPC scenarios, you grant network user permissions at the host project level, potentially with conditions to limit access to specific subnets. The auditing commands help you verify that permissions are correctly assigned and identify any overprivileged accounts. Complete security architecture. Now let's see how all 5 layers work together in a complete security architecture. This isn't just about individual controls, it's about how they complement each other to create comprehensive protection. External threats hit CloudArmor first, then flow through firewall rules that segment your network. Internal communications use Private Service Connect for granular API control, while VPC service controls prevents data exfiltration. IAM ensures only authorized people can modify these controls. Notice how each layer addresses different attack vectors. Layer 1 stops lateral movement, Layer 2 blocks external attacks, Layer 3 prevents data theft, Layer 4 controls API abuse, and Layer 5 manages insider threats. This is defense in depth. Multiple independent layers that work together to protect your infrastructure and data. Key exam takeaways. As we wrap up, let me give you the critical exam tips that will help you succeed on the GCP Network Specialty Certification. For comprehensive security questions, always think defense in depth. Never rely on a single control. When you see data exfiltration scenarios, VPC service controls is almost always the answer. Remember that service accounts are more secure than tags for firewall targeting. Private Service Connect is the modern approach compared to private Google Access because of its granular control. And always apply the principle of least privilege. Choose the most restrictive option that still meets the requirements. These patterns appear repeatedly on the exam, so mastering them will significantly improve your score. Good luck with your certification.